In this lesson, we're going to learn about a completely new type of series. This series is called an alternating series. And what an alternating series is, it's basically a series whose terms will alternate between being positive and negative. So a very, very simple example of this is actually the alternating harmonic series. You guys all know that the harmonic series is just the sum 1 over n. So if we were to take that series, and instead of it just being the series, 1 plus a half, plus a third, plus a fourth, and so on, if we were to ask it to alternate, if we wanted it to be 1 minus a half, plus a third, minus a fourth, plus a fifth, what we could do is we could do the sum of negative 1 to the n plus 1 over n. And the idea is that by sort of including this negative 1 to the n plus 1 factor in your summation, you're basically saying that when you input when the value of n that we're using, when this thing is odd, well, let's hear when n is odd, n plus 1 would be even, so then that's going to make that one positive. But then when you input an an even value for n, the even value plus 1 will be odd, and those ones will be negative. So basically this negative 1 to the n plus 1 is basically going to cause this thing to alternate between being positive and negative, and that's what it means to be an alternating series. Before I get into the alternating series test, I did want to point out a few different ways that things can be made alternating. So I suppose I call these, like alternating factors. I'm out of practice on this. Alternating factors. So the most common one is something like negative 1 to the n. Note, up above I use negative 1 to the n plus 1. The difference between those is basically whether your series is going to start out positive or start out negative. We've discussed before, sometimes sequences or series will start with n being 0, sometimes will start with n equals 1, sometimes with n equals 2. You really just need to pay attention to those things. But when you have negative 1 raised to a power like this, you're going to end up with an alternating series. One of the more interesting ways of doing this, and it's a kind of a favorite of mine, is actually the cosine of pi n. And I kind of like it because it makes series look a lot more complicated. But if you think about it for a minute, what happens when we put in 1 for n? When we put in 1 for n, this becomes the cosine of 1 pi, which is negative 1. When you put in 2 for n, it becomes the cosine of 2 pi, which means you've got positive 1. When you put in 3 for n, you've got the cosine of 3 pi, which is back to being negative 1. This is basically just a really fancy version. This thing is the same thing as negative 1 raised to some power. And this is actually a good place for us to think about this. When we put in n being 1, I needed it to be negative 1. When I put in n is 2, I need it to be positive 1. And so it would make sense here to use negative 1 to the nth power. When you see cosine to the pi n, it's going to end up meaning negative 1 to the n. It's just another way of showing that something is alternating. So when you have a series that has this alternating factor in it, it means it's an alternating series. And fortunately, with these alternating series, we have an alternating series test, which is actually very, very easy to apply. When you've got an alternating series, very easy to find out if it converges or diverges. And we'll see how next. So now, suppose we've got an alternating series, and we want to figure out, how can we determine whether this thing converges or diverges? There are basically 3 things that are required for the alternating series test. So this is sort of going to be, and if these 3 things are true, then we'll be able to say the alternating series converges. So first, take a look at the structure of this expression. Notice that I'm breaking it. I'm almost breaking it into 2 parts. There's a sub n, which is the sort of the series part, and then I'm sort of separating off the negative 1 to the n. So I'm saying, imagine you've got an alternating series, you've got kind of the alternating part, this part here that's actually making it alternate, and then the a sub n is sort of the series part, the thing that's actually doing something, right? So let's look at what the requirements are for the alternating series test. The first requirement is that we need a sub n plus 1 to be less than a sub n for all n greater than some value m. And what that basically means is that beyond some point m in the series, like maybe it's the first term, maybe it's the 5th term, maybe it's the 20th term, beyond some point, you will find that the n plus 1th term is smaller than the nth term. In other words, these terms are getting smaller and smaller and smaller as we go along. Now we know normally that's not enough to say that something converges. It's not enough to just say, oh, it's getting smaller. But for the alternating series test, that's one of the requirements. The second requirement here is that we need the limit as n approaches infinity of a sub n to be 0. Now again, on its own, that is not enough for any normal series to converge. But if we combine that with sort of our first requirement here, that the terms are getting smaller, our second requirement here, that the terms are going towards 0, and the third requirement, which is sort of a silly one, but I throw it in there because it's important, that the series needs to alternate. Now I know we set up here like, hey, consider that you have an alternating series, but dude, just don't forget, it's not enough for either one of these things to happen for any normal series. We need them to happen and be an alternating series. If those things are true, then the series converges. Okay? I don't ever use the alternating series test to show that something diverges. Part of the reason for that is that sort of like if the terms aren't getting smaller than one another, it's probably failing the nth term test for divergence. If the limit as n approaches infinity of a sub n is not 0, then it's failing the nth term. There are other tests to tell you this thing diverges. If you want to show it converges, that's really what the alternating series test is about. So first, the terms have to be getting smaller, the terms have to be turning into 0, and the series has to alternate. If that's all true, then your series converges by the alternating series test. So we'll take a look at an example here. Let's say we want to determine the convergence of the following series. So you'll notice in this thing, hopefully, that the numerator of this is basically giving us our alternating portion. Like we can see that this thing is alternating. In some sense, the basic part of this series is the 1 over the square root of n squared plus 1. Like that's sort of what this series is, but it's alternating because you've got this cosine of n pi in the numerator. Right? So what we're going to try and do here is we're going to try and use the alternating series test. Right? And I sort of gave my steps on the previous slide in the wrong order. I usually check to make sure it's alternating first. It's kind of a silly thing. But first, it is alternating. Check. Second, is a sub n plus 1 smaller than a sub n? Right? And we can either do that formally or we can sort of do it informally by sort of looking at this thing and saying, if I take a look at this thing, when I plug in a larger value for n right here, well, what happens, right? When I plug in a larger value for n, the denominator gets larger, and because the denominator gets larger, the entire rational expression gets smaller. And so because of that, I can pretty clearly conclude that this is true. There are some problems where that's a little bit more complicated, and you may need to set up an inequality to show that, but for the majority of these problems, it's going to be a pretty straightforward thing. You're going to be able to see that the terms get smaller, and it works out okay. Your third step, is it true that the limit as n approaches infinity of a sub n, there's a horrible infinity, of a sub n is 0? Is that true? And so we should take a look at this. We should look at what is the limit as n approaches infinity of 1 over the square root of n squared plus 1. Remember, we really don't pay attention to the alternating part. We're just talking about the non-alternating part. Is that turning into 0? And this, again, is pretty clear. As n approaches infinity, the denominator of this thing is becoming absurdly large, which means that this whole thing is effectively turning into 0. So this last thing is true as well. Therefore, our series converges by the alternating series test. It's a pretty simple test to use. So let's take a look at another example here. Step 1, is this thing alternating? Yes, it's definitely alternating. We can see that in this -1 to the n plus 3 factor in the numerator. When you plug in odd values for n, this power is going to be even, so it's positive. When you plug in even values, the power is going to be odd, which means it's going to be negative. It's definitely an alternate between being negative and positive. Second step, is it true that a sub n plus 1 is smaller than a sub n? And this one is actually a little bit more complicated. You've got this sort of n squared minus n factorial in the denominator. It's a little bit complicated. We could set up an inequality for it. The other thing that we can do is we can just sort of explore what happens as we plug in values of n. And again, I'm going to sort of ignore the alternating part for a minute. But when we put in 2, right? If I've got 1 over 2 squared minus 2 factorial, you're basically looking at 1/2. Your next term in this thing, when you put in 3, you'll have 1 over 3 squared minus 3 factorial, which is 1 over 9 minus 6, so 1/3. Next up, you'll have 1 over 4 squared minus 4 factorial. Let's see, that's 16 minus 24, so that's actually negative 1/8, right? As we go further, we have 1 over 5 squared minus 5 factorial. Then hopefully you guys are going to see that this is going to start to kind of get out of control. The denominator of this thing is now 25 minus 120. That's negative 95, right? And so the idea is, initially, and it's actually interesting, this thing actually was sort of steadily getting smaller the whole time. We didn't realize that at first, but we can see when we write down a few of these things, as this goes on, these factorials are just going to get huge. The squared is just not going to be able to stand up to it. These terms are definitely getting smaller and smaller and smaller as the series goes on, right? For my third part of this, for the third part of this, there we go. For the third part, do we have the limit as n approaches infinity of a sub n do we have this limit equal to 0? This one, again, is pretty clear. Also, based on what we showed here, as we're plugging in larger and larger values for n, these terms are definitely tending towards 0. So we have that the second step is true, the third step is true, therefore this thing converges by the alternating series test. Some of you may be wondering whether this is really an alternating series, because you'll notice that it was positive, positive, negative, 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 negative. If we apply this alternating thing to it, the beginning of it might not be perfectly alternating, but one of the ideas is that once we get past a certain point, it's going to begin alternating. Once we're past this point right here, all of these things are negative, so the alternating part is going to pick up and make sure that it continues to alternate. And so because it alternates, we can use the alternating series test. I know this video is already a little bit on the long side, but I just wanted to point out one other thing. This series may look like an alternating series, but I'd like you to pause the video for a minute, take a minute, and look at why it's actually not an alternating series. When you look at it, what makes you think that it might be alternating, and what lets you see that it actually isn't alternating? I would say the thing that makes this look alternating is that you've got negative 1 raised to a power. But the interesting thing is, what happens when we take that power? What happens when we take negative 1 to the 2n plus 1? What happens when we input integers to n? Well, when you multiply by 2, they become even. And when you add 1, they become odd. So what's interesting is that this thing here is actually always negative 1. It doesn't switch between being positive and negative because the exponent is always odd. You'll see the same thing with things like negative 1 to the 2n. Negative 1 to the 2n, that 2n is actually always even, so negative 1 to the 2n is actually always positive 1. What if we did something like negative 1 to the 3n? Does that alternate or not? Pause the video, take a minute, think about that. Does that alternate? The answer is yes, because when we put in an even or an odd, you put in an odd for this, the power is going to stay odd. You put in an even, it's going to become even. Another way of thinking about that is that you could rewrite this as negative, not negative 3, got a little ahead of myself. You could rewrite this as negative 1 cubed to the n, which is basically negative 1 to the n. We can see that this is going to alternate, whereas these two guys up here are not going to alternate. So just be aware of that as you look at these problems and as you look at things that might appear to be alternating.